Yeah, absolutely. Oh, that's gonna say.
All right, when do we,
Just hand it to somebody and say, here, experiment and make sure the roof's open first.
Yeah.
So what is that place where people are gathering? So AAL now has its own auditorium?
oh, yeah, that, this is, Baker Wetlands Discovery Center.
Okay,
So, right, we're down at by the wetlands. They built a real nice facility here. In return for giving up some property to build the bypass around town. So, we've been out here for a while now.
excellent.
It is.
I don't think we had any, trying to remember what it was like when I was in Lawrence, but I don't think we had any physical facilities.
Oh.
Just Lindley.
Just
Yeah.
that little room at the top of the stairs in Lindley, yeah.
Yeah,
Okay, thank you. All right, well, let's go ahead and get started.
Okay.
So I'm happy to welcome back Dr. Humberto Campins, who is an expert in comets and asteroids and other small bodies in the solar system. And one of his interests is the role these bodies played in possibly delivering water and organic molecules back to the Earth. And fittingly, since he studies asteroids, he has an asteroid named after him, 3327 Campins. So so I'm confused. In February, in 21, Steve introduced you and said you were a graduate. You graduated from KU in 77, and then I saw somewhere else 78. So I'm not sure.
77.
Okay.
Yeah, I
So,
graduated in May of 77.
right. So he's an alumnus of KU. He's also an alumnus of the Astronomy Club. He was a member when he was going to school here. He's gone on to much bigger and better things since then. But in February of 21, he talked to us a little bit about the OSIRIS-REx mission, which he's a project scientist on. And that mission to the asteroid Bennu has returned with samples, which was the purpose of the mission. And so I asked Dr. Campins if he would be interested in, doing a follow-up presentation and talking a little bit about the results of the mission and what they learned about the asteroid and what they're learning about the material that came back. So he's currently the Pegasus Professor of Physics and Astronomy at the University of Central Florida, and he's also the director of their planetary and space studies group, space science group. So without further ado, Humberto, I'll turn it over to you. And
Okay, let me actually stop sharing so you guys see me. Greetings, and I have a question. Is there anybody who didn't see my 2021 presentation? Because if everybody saw it, then I'll go through the introduction more quickly. If not, I wouldn't want to have anybody who's not seen that one be kind of left with a too short of a presentation.
I don't remember whether I saw it or not.
yeah, I'd go ahead and,
Okay.
and give us a.
Okay, I'll go through the introduction relatively quickly, but so that nobody's been left completely without a background. Okay, so
you.
let me go ahead and share my screen again. All right, so this has been a wonderful ride, the most fun project of my career. I got invited in January of 2010 to be part of the team that wrote the proposal, submitted it, and we were selected in mid 2011, and it's been a wonderful ride. So the mission had four main justifications in our proposal to NASA, revealing solar system history by bringing back a sample of a very primitive asteroid and trying to understand how asteroids and planets formed, mitigating impact hazards so that Bennu is actually the most potentially hazardous asteroid. I'll go into that in a little bit more detail later, but the main point is if we have to deflect Bennu or another asteroid like it, all of the information from this mission is going to help us mitigate future impacts. And let me also clarify that at this moment, there are no asteroids that are threatening Earth with an impact. But if one were to do so, then we want to know as much about them so that we can deflect them. The enabling human exploration, it is very likely that humans will stop in the moons of Mars on their way to Mars, and it is also possible that we're going to be having human missions to asteroids. So the trip to OSIRIS-REx to Bennu is going to be enabling human exploration. The moons of Mars are most likely captured asteroids, so the more we know about asteroids, the easier it will be for us to predict what we will find on the moons of Mars. And then developing a space economy. It turns out that because putting things into orbit is so expensive, then at some point, if you were to mine an asteroid for the most precious material outside of the Earth's atmosphere, which is H2O, which can be broken down into hydrogen and oxygen, will be great fuel and can be used for other things, but its main use will be fuel. If the moment, so because it is so expensive to launch things, the moment that mining an asteroid and delivering that fuel to the Earth's orbit, all Earth's orbiting satellites would rather buy the fuel from a cheaper source than to fuel up before they get launched. And therefore, there will be a self-sustaining space economy where the fuel would be produced from the water extracted from the asteroids, and it would be delivered to the Earth's orbit. So you'd have a remarkable marketplace where you have all of your clients and all of your producers in space. And so don't you guys wake up every morning wondering what OSIRIS-REx stands for? Even I don't, but I memorized it from all of these years working on it. But it stands for Origins, return and analyze the sample of a pristine carbonaceous asteroid, spectral identification or spectral interpretation to map the chemistry and mineralogy of the surface, which we did in great detail. And we had some interesting surprises that I'll discuss with you. Resource identification, identify resources for future asteroid mining. Security, to measure the potential hazardous asteroid in case we need to deflect it. And Regolith Explorer was added. The team, before I joined them, had submitted the proposal and made it to phase A, but NASA told them that the budget was too big for that category to submit the proposal to a different category, which was the new Frontiers missions. And so that's under which we got funded. So Regolith Explorer was added between the Discovery and the New Frontiers proposals, and it was to touch and study the surface in detail. And we did that too. So I was surprised and felt somewhat naive when I joined the team, and I realized that this was going to be only the fourth time that NASA was going to bring back a sample from above the Earth's atmosphere. First time was the Apollo mission. The second time was the Genesis mission that brought back samples of the solar wind. Third time was Stardust, where we picked up particles from the tail of a comet. And then OSIRIS-REx brought back the sample of a primitive asteroid. So just to remind us where most of the asteroids are between the orbits of Mars and Jupiter. And they're here in red, they're here in green. And the red ones are the near-Earth asteroids, the asteroids that come close to the Earth's orbit or cross it. And it's just a little bit of a reminder of how many asteroids, the majority of them between Mars and Jupiter. Some of them are in the Trojan clouds ahead and behind Jupiter in its orbit, and then the near-Earth asteroids in red. then here's also a little bit of a summary of all the asteroids that have been visited by spacecraft. And very few of them, as a matter of fact, only 4 have been visited in rendezvous missions. And so one of them was Hayabusa that went to asteroid Itokawa and brought back a sample in 2010. And then Hayabusa 2 went to asteroid Ryugu and actually got to asteroid Ryugu a few months before OSIRIS-REx got to asteroid Bennu. So we benefited by a collaboration between the 2 space agencies from data that Hayabusa 2 had obtained on Ryugu before we even got to Bennu. And that also helped us plan a little bit better our sampling maneuver. And so this is what we expected Bennu to be from Earth-based observations. Size about 500 meters in diameter. We knew about its rotation rate and sense from the radar observations done from the Arecibo radio telescope. We knew roughly that the bulk density and the albedo, it reflects, Bennu reflects only about 4.5% of the light that falls on it. And it was a relatively unusual spectral type B that stands for blue, and it was associated with CICM chondrites, which is indeed one of the things that we found. So that is what we knew about it before we got there. This is the asteroid Bennu in December of 2018 when we first got there, and we realized that a lot of what we had expected was indeed the case. So this is in 2018 we made that this set of images that showed its rotation and its surface structure. We collected the sample in October of 2020, and you may wonder why we went to an asteroid if we have, so many meteorites that come from an asteroid. And one of the reasons for sample return from an asteroid, even though we have meteorites that we know come from asteroids, is that in the 2 cases that have been studied in enough detail, we've determined that 99.9% of the material that enters the atmosphere is lost before it makes it to the ground. So we only know that 0.1%, and we don't know what was lost. So that's one reason for sample return. Another reason is that we can have state-of-the-art analytical instruments that are too heavy to put on a spacecraft that we can use on the sample return of this pristine sample that we know has not been affected by the atmospheric entry. And also because we want future scientists who may invent new instruments and have new hypotheses to have access to the sample. In fact, 2/3 of the sample is being archived by NASA, and only 1/3 of it is being analyzed by the teams that have been assigned. And another reason that we want to study these asteroids is because we'd like to understand ancient Earth. Asteroids and comets have delivered water and organic molecules to the early Earth, and the record of any organic molecules on the Earth before life form have been destroyed by geologic processes, by life itself. So Bennu contains the type of organic molecules that were on Earth before life formed. And so the samples of Bennu are helping us understand how life may have originated on Earth and possibly on Mars, the moons of Jupiter, planets around other stars. So the step between a complex organic molecule and the first living cell is not understood. If we can figure out that with the help of the samples that we brought back from OSIRIS-REx, it would be very important for us to know where to look for life outside the Earth. And as I mentioned earlier, the development of a space economy, asteroids are ideal resources for developing the space economy. The moment that fuel from asteroids is cheaper than launching them from Earth, then you can have a cheaper source of fuel, and the market is going to favor that source. In addition to the fuel, the communication and other satellites could be 3D printed in space with asteroid materials. So imagine instead of having to put a structure, for example, like the Hubble Space Telescope, into to have it fold onto itself and put it into this relatively small tube and shake it and then send it up there. If you could print most of that structure up there, it would be not only cheaper, but it would be with materials and techniques that would not even have to withstand 1G on the surface of the Earth. So I think there's a great potential for really remarkable structures out there for collecting solar energy, for other applications that could be done once we can mine the materials above the Earth's atmosphere. Another set of images, just to remind you of what Bennu is like, a rotation every 4.3 hours. And we got there, and some technical details, I'm not going to spend time on that. But we got there, and we were so happy because what we predicted had become indeed true in most of the quantities that we had predicted the characteristics of the surface of the asteroid. You know, the size turned out to be correct, the rotation rate, the shape. And so we were so smug. We were so just proud of ourselves. We are so smart, you could just die. And it turns out that we did predict all these things that turned out to be the correct ones. And we also, for good reason, expected areas of coarse sand or pebbles on the surface of Bennu. And so, for example, one of the reasons why we predicted that, this is asteroid Itokawa that the Hayabusa 1 mission had been to. And you can see these areas that are smooth and have relatively few rocks. And we said, nice beaches where OSIRIS-REx can come down very safely and do the sampling and not have to worry about hitting any rocks, right? And so here's the surface of Bennu. And this is very typical of the entire surface here. This rock here is approximately 4 meters, a good 12 or 14 feet high. So it's just not what we had hoped for. So, and we also found that the asteroid was throwing out particles into space. This was a very exciting discovery, and it turned out to be not a threat to the spacecraft. So I can tell you more depending on how much time we have at the end. But so these were the two biggest surprises upon our arrival. We then had to reprogram the spacecraft because it had been programmed, excuse me, it had been programmed to collect the sample using just an altimeter and go down into these beachy areas with no big rocks and collect the sample. And it turns out that we had to do an extensive campaign to do the sample selection, and we had to at the same time reprogram the spacecraft to do a completely autonomous reconnaissance of the sample site that we had chosen, and be completely autonomous as it went down. But instead of with just an altimeter, it was going to be making corrections depending on what the images were showing it. So we narrowed down the sample, the candidate sample sites to these 4. And we ended up selecting the first one, which I will tell you in a second. I had voted for the second one, which had fewer big rocks around it. The rest of the team preferred this one, and they were right. The navigation team felt like they could put the spacecraft safely in the middle of this one in spite of all these hazards around them. And so we succeeded. So this was called, all of the structures on Bennu were given bird names, either mythical or actual natural birds. And Nightingale was the one that got selected, where we sampled from. And here's some images of Nightingale with more and more detail. So you can see that there's loose material. This is the middle of an impact crater. And but instead of, initially the navigation team had asked us, I was on the imaging team, and they had asked the imaging team, please give us a really nice smooth area of about 150 feet, 50 meters across. And after we saw the first set of images, we said, no such place. I said, oh, but the spacecraft is navigating so well, and we're such a good navigation team that we can put it down in half that size. And we went, bang, no such thing. And then they said, what can you offer us? And then we said, well, this is the best we can offer you. It's about 8 or so meters across, but with big rocks around them. And that's when they decided to change the way that they would, do the spacecraft would navigate autonomously as it was taking the sample. So this is the artist's conception of what the sample was going to sample maneuver was going to be like. And I bring it up because the artist drew the asteroid without any big rocks. This is what the navigation team expected, right? And we're going to come down at basically very low vertical velocity and 0 horizontal velocity, which is not trivial because this asteroid is rotating every 4.3 hours. And we're going to take the sample and fire the thrusters and move away. And I like to emphasize a little bit the artist's conception in the proposal, and then the artist's conception after we got there and did the sampling. So this is the one in the proposal and for which we got funded. Had we put this one, which is much more realistic of what it was like in our proposal, we probably wouldn't have gotten funded by NASA. Anyway, so here are a few images that illustrate how it happened. So this is the mechanical arm with a sample collection mechanism at the end, and it touched the surface and it went down about 10 centimeters. It fired these nitrogen bottles that the spacecraft had so that it would fluidize the dust and bring it into the collection canister. And then this is another view of what we think happened. These illustrations were done after the fact. And we actually did it. We did 2 rehearsal maneuvers, which showed a few areas where we can improve the software. Those improvements were done, and we ended up touching down within 75 centimeters of where we intended to touch down, which is remarkable. This is the actual area where the sample had touched, and here are some images of the sample maneuver, and the head reorients itself just before touchdown, fires the nitrogen bottles, and picks up the material into the canister. Here's another set of images where you actually see the shadow of the mechanical arm as we're going down towards the sampling. So you can see that there's all kinds of material that is lifted by that maneuver and by the nitrogen bottles that get fired. And the sample was immediately stowed. And the reason is, once we took images of the sample head, we realized that there was a big particle that was obstructing the flap from closing, and material was drifting out of the sample canister. And so instead of doing a maneuver that we intended to do while the sample was, the arm was extended, that would have given us the mass of the sample. We had planned that maneuver. Dante, the head of the mission, decided to stow the canister immediately and not lose any more material. We would know how much mass we got once we got back to Earth, but any maneuver to try to measure the mass when we were out there was going to create more mass loss. So that was decided back then and saved more particles from being lost. These are some interesting images of the crater, and I won't go into too much detail, but it turns out we learned a lot by studying the crater and the effect that the spacecraft had on the soil after the collection. And if we have time, I'll tell you a little bit of the fact that that was one of the sets of evidence that revealed that there was a layer of fine material under all of those rocks, which one of my colleagues had predicted, and then we published a paper discussing that layer. Okay, all right, so this is what I just mentioned. I presented this a year ago, and the first author of the paper is my colleague, Bo Bierhaus, but he was not attending that meeting, so I presented this. And the bottom line is that based on the morphology of craters and other data sets, we thought that there should be a layer of material right under the surface, the rocky surface of Bennu. As a matter of fact, here's one of our figures. So here is the surface rocks, and you see essentially almost no fine material at all. But if the craters of different sizes are studied, you see that there is a layer of fine material under those rocks that has a depth of about 1 to 4 meters, and that craters that are large enough will penetrate through that layer and reveal rocks below it. So there's like rough surface, fine layer of fines, and rough subsurface. And that was one of the cool things that we were able to demonstrate after we did the sample, and we were able to study the sample site and what happened after the sample was collected. So the spacecraft delivered the sample back in September of 2023. So we're all excited about that. Here's an image of the capsule that is been detached from the spacecraft. So this is one of the cameras on OSIRIS-REx, and it took an image of the capsule being, after it was detached and was headed towards Earth. So now OSIRIS-REx has become OSIRIS-APEX, and the OSIRIS-REx team is analyzing the samples. The OSIRIS-APEX team is preparing to encounter asteroid Apophis, which is going to come near the Earth in 2029. As a matter of fact, it's going to be Friday, the 13th of April of 2029. And OSIRIS-REx is going to come and join orbits with Apophis. And Apophis is going to come between the geostationary communication satellites on Earth and the surface of the Earth. So it's going to come really close, but we know it's not going to hit. We know the orbit of Apophis quite well. But it's going to be a great opportunity for OSIRIS-REx to then follow up and study a different asteroid. We no longer have the capability of bringing samples back to Earth, but we have all of our cameras, all of our spectrographs operational. So this mission is, it's an extended mission. NASA approved it and funded it, and it's got mostly the younger generation. The principal investigator was the head of the imaging team on OSIRIS-REx. We have a lot of young people involved with that. So it's going to be a very good opportunity for them to develop their skills and maybe propose and operate future missions. This is the capsule once it arrived on the Utah desert. Here's the parachute. Once I saw the parachute deploy, I said, the capsule is safe. And for me, it was a very exciting moment. This is the team, Dante and a couple of the other team members looking at the capsule, and then it got picked up and taken to a facility nearby and eventually ended up in Houston. So the sample arrives in Houston. That's Dante, all excited. I'm surprised they let him bring in his cell phone into the clean room. Anyway, and here is the sample canister before it got open. And I got a whole bunch of messages from acquaintances, some relatives, about this thing in the news that said mysterious black dust found inside of the capsule of OSIRIS-REx. And I had a hard time not just blowing this off, but I did have the patience to say, okay, guys, before you sent me this or before you read this, what did you think was going to be the case when we opened that capsule? We went to a dusty black asteroid and we touched the surface and we fired a nitrogen bottle that kicked up dust everywhere. When we bring it back and we find black dust around our canister. How mysterious can you get? We're going to have to hire Sherlock Holmes to figure that one out. And anyway, that's the age of, people's 6-second attention and social media and very poor journalism. Anyway, so initially there were 2 of these screws that would not come off. And so they had to they basically depress the flap, and tweezer out enough material for us to declare victory. Our threshold mass was 60 grams. They were able to pick out 70 grams. We declared victory. And then eventually the people at the Kennedy Space Center were able to open the canister and we got the rest of the sample. We have 120 some grams. We will be given 10% of our sample to, well, I'll discuss that in more detail later, but we will be giving, or we have given 10% of our sample to the Japanese Space Agency. And they gave us 10% of their sample for us to analyze in our labs. So that's one of the good things about international collaboration. You end up getting samples from 2 asteroids for the price of 1 mission. Okay, so these are different components of the sample that was being analyzed. The threshold of 70 grams was reached, and then the rest was extracted from the canister once it was open. Here's some examples of things that got that are being analyzed: water-bearing clays. We have sulfide mineral plates. We have iron oxides. We have a different morphology of the iron oxide. And so here's a little bit of the predictions of what we expected in our sample from before we got it back. We had a size range of submicron to 3 centimeters because the largest hole in our sample head was 3 centimeters, and we ended up getting one that was 3.5 centimeters. So that went in through the small axis. If it had been, if it had gone in, if it tried to go in on its largest axis, it wouldn't have been. But anyway, so we got the largest particle, larger than we expected. Hydrated minerals, mostly silicates, carbonates, magnetite, which is a form of iron oxide. We had sulfides, which are not spectrally active, but inferred from the morphology of analog meteorites that have been studied in our lab. When we found organic compounds. And it's interesting because I got invited onto this team in January of 2010, and I attended my first meeting in February of 2010. And they said, listen, we got comments from back from NASA for us to incorporate into our next version of the proposal. And one of their concerns is that we are going to Bennu to bring back samples of organic material, yet no organic molecule or no organic material has been unequivocally identified in an asteroid. And I raised my hand and I said, yes, it has. My colleague that is sitting over there as co-investigator on one paper, and I'm first author on another paper, and the two teams basically confirm each other. They did observations of asteroid 24 Themis throughout its orbit, and we did observations as it rotated throughout one full period, and we both detected organic molecules and water ice. And they said, oh, we want those papers. And we said, sorry, we can't give them to you until the end of April because they're being embargoed by nature. But anyway, so they were very pleased that we, without them knowing, they had invited 2 team members who were solving their main science question, or main science objection by NASA. in terms of the type of lithologies or the type of rocks that we expected them to be similar to CI and CM meteorites, and that's true, but it's not identical to either. So we could have yet another type of material that is very similar to CIs and may have some characteristics of CM, so it's kind of in between. So we did find what we expected there, but it's even more interesting. We were hoping, and yours truly especially, were hoping to find, and that may still be the case, we're still looking, to find igneous material in on the surface of Bennu, like HED meteorites that come from Vesta. And that's because our cameras and our spectrographs identified these very bright objects on the surface of Bennu, which I had warned the team were likely, and they had basically dismissed my argument, and I'll tell you more about it later. But I'm hoping that we found chunks of another asteroid on Bennu, and nature gave us an amazing gift, which was those chunks were from the easiest asteroid to identify in the whole asteroid belt, because Vesta is so unusual. Anyway, so we did, and we're hoping that in the sample somewhere there's a little bit of grain that came from asteroid Vesta. So we would have sampled 2 asteroids in one sampling maneuver, and then with the help of the Japanese, we'll have samples from Ryugu, so we would end up samples with 3 asteroids with one mission, but we still haven't found those yet. Some of the properties of that were from meteorites we predicted, for example, magnesium to sodium to phosphate crusts, we did find, and we were expecting monomineralic centimeter scale carbonates, but those pieces would be so large that maybe we just missed it, but we're still looking for them. And ejected centimeter scale Pleiades particles that would have been basically the type of particles that the asteroid was ejecting that we saw when we got there in January of 2019. We're still looking for them that may help us understand the mechanism that was ejecting particles when we got there. Implications for planetary science. A few details here. I don't want to go into too much into the weeds, but Bennu samples are hydrated organic rich remnants of the early solar system. The bulk elemental abundances are essentially same as the sun and as CI chondrites, which are the most volatile element abundant meteorites. They're believed to be the most primitive meteorites in our collection, in the sense that they contain the largest fraction of volatile elements that if the meteorite had been heated, it would have lost. So except for ices and noble gases, which we can measure on Bennu, and we have no evidence of ice yet, but the bulk elemental abundances are exactly the same as the sun as the CIs. So OSIRIS-REx samples represent the largest pristine reservoir of the most primitive material in the solar system that we have access to. So that's important. We sample the spectra from the global asteroid, which is a B-type asteroid. It has a negative visible near-infrared slope. That means it reflects more blue light than it does red light, and that's why it was called a B for blue. The more positive slope than okay, so the samples don't have the same spectra as the rest of the surface. So we are puzzled because we brought back the sample, and the sample looks kind of neutral, but not very blue. Yet the asteroid as a whole, when you look at the entire disk and even smaller parts of that surface, it looks blue. We have some morphologies that are similar in our sample to the Bennu boulders that I showed you earlier. So there are 2 main types of boulders, and they're represented in the little pieces that we brought back, 2 different types of morphologies. So there's a fractal-like fracturing of the big boulders that gave us the pieces that we brought back. We don't have any evidence yet of the carbonate veins that we observed on the surface of Bennu with the spacecraft. And we have these magnesium sodium phosphate layers on the surface or skin coating that it is very interesting, and we need to understand the geochemical processes that may have deposited that hydrothermal, igneous, vapor deposit. And we also have very high concentrations of organics, and we have a combination of aromatic, which are ringed, and aliphatic, which are linear molecules that in their CH bonds. So the people that are analyzing the organics on Bennu are really excited. They're finding all kinds of stuff that they keep telling me we can't say anything until we publish. And so I'm hoping that those publications will be coming out soon. But it's a very interesting asteroid in the sense that it will give us a very large sample of organic molecules that were delivered to Earth by asteroids. And as a result of that agreement between the Japanese Space Agency and NASA, we already got the 10% of the Ryugu sample that was selected by what was collected by the Hayabusa 2 mission. And by the way, my hat is off to the Japanese. They got there in just a matter of a couple months. They did their first sampling, which was successful. And they were not satisfied. They then shot a projectile onto the surface of Ryugu, created a crater, and went down with the spacecraft, and in a separate chamber of the sample, collected the sample from the fresh sample that had been exposed by this crater from this projectile that they had shot onto the surface of Ryugu. So their risk posture was much higher than that of OSIRIS-REx. And so another thing that I wanted to mention is that we did this mission on schedule, and it was a very complex mission, and under budget. We returned $52 million to NASA at the end because we did not need them. NASA gave us a certain amount of money to have in reserves, and we, at the end of the mission, we had 52 million left, and we returned that to NASA headquarters. I don't know if this was the first time ever, but I'm proud to have been part of that team. What next in terms of my projects? I'm involved with the ERA mission, which is launching from the Kennedy Space Center on a SpaceX launcher in October of 2024, and it'll get there in 2026, and I will be helping them with their hyperspectral imager. And we are part of a proposal that's submitted to NASA over the last time New Frontiers was competed. We submitted a proposal and we ended up second. And there should be a new call in 2026. And so the team is submitting the proposal for CSER, which is a comet surface sample return. And a lot of the people on OSIRIS-REx will be on CSER if it gets selected. So I'm looking forward to that. And here's the CSER is being led by Cornell University, and it has the participation of a number of institutions, including the University of Arizona. And in conclusion, OSIRIS-REx returned the sample from asteroid Bennu on September 24th of 2023. It's a potentially hazardous asteroid and also the target for asteroid mining. Ongoing sample analysis, especially for prebiotic molecules relevant to origin of life on Earth. And now OSIRIS-APEX, it's headed to asteroid Apophis in 2029. And I am looking forward to that because the imaging team asked me to be part of them in 2029 when they get to Apophis. So I get to have fun with yet another asteroid. And so that's it. Okay, so let me open this for questions. So let me stop sharing. And I see three, how to call that, figures that are not well defined because they're backlit. I think that they're doing that to practice their interrogation techniques for Guantanamo.
So what type of asteroid is Apophis? Is it
It's an S-type asteroid, and is actually the most common type asteroid, and the one that we're most likely to have to deflect if it were to come close to Earth. So the two main populations of asteroids in the asteroid belt and near the Earth can be divided into primitive, which are Cs and Bs, and S types, and they're about equally abundant. The S types may be a little bit more abundant, and so in the case of asteroid Apophis, it is much brighter. It's about 4 or 5 times brighter at the surface, and it's got an albedo of 20% instead of 4.5%. So the cameras are being adjusted so that they can take much shorter exposure than on Bennu, because they're going to have 4 times the light. But it should be a lot of fun, and it should have a lot more spectral features than Bennu. Primitive asteroids tend to not have as many spectral features. S-type asteroids have more. Any more questions? Oh, it looks like somebody, Barbara raised her hand.
Yeah, I'm trying to understand what it means to have 60 or 70 grams and whether that's limiting. Can you do everything you want to? Can you do isotopic analysis as
Yes.
well as the
The,
broad
the,
analysis
the,
described?
the sample analysis team has been subdivided into groups that are doing physical analysis, chemical analysis, isotopic, organic. There's a whole, and then of course the non-destructive techniques are favored first, and any destructive technique gets put at the very end of the process. And so yeah, and this is great. I mean, the Hayabusa 1 brought back a few micrograms. Hayabusa 2 brought back 5 grams, of which we get half a gram, which it's a lot more than what we gave them, but that's fine. We made the agreement knowing that we were likely to bring back more, right? But this is more than enough. These techniques for analyzing at the nanoscale level, the chemistry, the mineralogy, the isotopic composition, the volatiles that come off of these materials, because while you're analyzing, they're outgassing. That gets measured by a mass spectrograph, and so there are all kinds of very interesting things that are being done. And the threshold was 60 grams. We were going to declare victory if we brought back 60 grams, 50 grams, 60, I'm sorry. And we brought back more than twice. So, and not only that, personally, I expected just dust. I did not expect coherent 3-centimeter chunks, because this thing was subject to 20 Gs on its entrance to the atmosphere. They were not suddenly 20 Gs. There was a gradual thing, but still, I was thinking, boy, that material has got to has to withstand 20 Gs. So that's a good question, and the answer is yes. We got enough and more, and some interesting surprises so far.
So the more detailed photographs of the asteroid look more like it was just like an accumulation of rubble as opposed to a solid rock.
And that is indeed the case. If you remember the images that I showed you of the sample head pushing into the surface of the asteroid, it turns out that we expected a certain amount of compliance. In other words, that the surface would allow us to go up to a certain depth, but we're also going to be measuring how much the asteroid was going to push back on the sample head, because it had a spring. And anyway, and if the spring was supposed to push the spacecraft away from the surface when it touched the hard enough surface, and if not, the thrusters were going to fire. It's a good thing the thrusters were automatically firing, because they determined that had we not fired those thrusters, the entire spacecraft would have been buried from just the 5 centimeters per second speed that we had touching the surface. We would, the behavior of granular material in essentially 0 G, it's like 1/100,000th of the gravity on Earth. It's like a fluid. And we didn't quite expect that. We expected those rocks to push back on us, and it just moved out of the way. And luckily enough, there was that layer of dust below the surface, and we were able to sample just fine. Why don't I, if you give me, I'll take 2 minutes, and let me share my screen again and tell you why I think that there should be pieces of Vesta on Bennu. And these, I had predicted based on a meteorite that fell on Earth in 2008 called the Alma-Ata-Sita meteorite. I had predicted that we could have different lithologies, different types of rocks on the surface of Bennu from different asteroids. And the team told me, no, Humberto, do not waste our time with something that is very unlikely, that it's at most 1 in 10,000 chance. I said, okay. Now, 4 people took me seriously. The head of the imaging team, the 2 main people on the spectrograph team, and one of my French colleagues who was on the team. And when we got there, one day I was walking by the office of Danny Della Justina, the head of the imaging team. She goes, Humberto, come take a look. And I said, what? And she shows me some of these images. And she said, didn't you say that we would have bright things and dark things on the surface of Bennu? I said, yes. She goes, these are not only much brighter than the rest of the surface, but they have weird colors. And so she said, she shows me the colors. And I go, that looks like an absorption near 1 microns. Can we get the spectrograph to tell us if they did scans over these areas? And the spectrograph people had spectra of 5 of these 3 rocks. And we quickly determined that these rocks were made of a type of lava that you can only find on the surface of asteroid Vesta, which was visited by the Dawn mission, NASA's Dawn mission, but they didn't bring back samples. So we determined that these rocks, and actually it turns out another 71 other ones that we found around the asteroid, were from Vesta. And so I am hoping that little grains from these things will be in our sample. And so that's my main punchline. And if I may be allowed one last question, and I will preface it by saying that some of my best friends are theorists. But the theorists had told us that this was impossible, that if there was a collision between 2 asteroids at the average speed in the asteroid belt, which is 5 kilometers per second, the impactors, the projectiles would be completely vaporized, and this would be impossible. And then it turns out that the theorists are having to go back and rethink this. And that's why I said that some of my best friends are theorists, and it's true. Just that I don't take them very seriously.
Wasn't Alma-Ata-Sita like 5 or 6 different lithologies?
Correct. And actually, I was talking to Peter Jenniskens, and he says that they have identified something like 12 different lithologies so far.
Oh, wow.
Yeah, and what prompted me to predict that Alma-Ata-Sita could have something to do with Bennu was that I actually did a study of where in the asteroid belt Bennu was likely to come from. And it was the Polana family in the inner belt. And when we looked at the orbit of Alma-Ata-Sita, it was essentially the same as that of Bennu. And so it likely came from the same part of the asteroid belt. So that's what made me think of this. And the meteorologist said, Alma had to sit as one case in 10 or 20,000. Don't waste our time, send him to Guantanamo, revoke his visa to Arizona, have him stay in Florida or in Cuba. And yeah, and I bit my tongue. I didn't say I told you so. It was pretty obvious.
Excellent. Well, thank you, Humberto. That was very interesting.
My pleasure, and it's a delight to be talking with you guys. As you all know, and as Barbara knows particularly well, my roots in Gainesville. I'm sorry, in Lawrence, Gainesville is where I worked at the University of Florida for 9 years. But my roots in Lawrence are pretty important. I mean, Steve Shaw, the Astronomy Associates of Lawrence. And my whole experience there just really shaped the rest of my career. And I'm still in close touch with Steve. As a matter of fact, I'm gonna go on a hike in Tucson a week from today. I'm flying to Tucson tomorrow morning. So it's just, it's a huge part of my life. I mean, and I'd rather be lucky than good, and I've been very lucky.
I was a little disappointed when I read Dante's book that there was no mention of you in the book, but
I'm not offended.
you have plenty to smile about after this mention.
Well, yeah, and my guess is that if Danny De La Justina were to write a book, she'd probably mention me. And the other thing that happened is that when these rocks were discovered, there was a list of papers that we had said, I have first dibs on this paper if we ever discover this.
Yeah.
And I had a paper on exogenic materials on the surface of Bennu. And so Danny said, you're gonna write the paper, right? And I said, you discovered these rocks, you write. So I'm a co-author, but she was the lead author.
Well, enjoy your trip out to Tucson.
Thank you. And hopefully I'll have a trip back to Lawrence sometime around this time of year. This is about the best time of year before it gets spring, before it gets hot.
Yeah, although we've had some weather the last few days, so.
Yeah, did that nasty storm affect you guys?
No, not really here. It was
Iowa and
southeast of Kansas City and northern Missouri and Iowa and up in Nebraska. Yeah, South Kansas and Oklahoma and Texas. We were kind of in the middle of all of it, but nothing too bad here.
well, good. I'm glad to hear that.
All right,
Yeah,
well, thank you very much.
Thank you.
Thanks.
My pleasure. My pleasure. And in the future, if you want to hear, thank you. And if you want to hear about ERA, or if we get Caesar, my other big project, which I am going to start in about a month, is a collaboration with the University of Coimbra in Portugal. They want me to start an asteroid and lunar surface group there. So I'm going this summer to check it out and to see how feasible it is. We asked for money from the European Commission, and if they get the money, then I can hire about 7 or 8 people there. And I'm also excited about that. So the amazing opportunities just keep showing up.
Excellent. Well, thank you very much.
Thank
Bye.
you.
Barbara.
Thanks,
Bye.
Humberto.
It's been a pleasure.
All right.
It's great to see you, Barb.
Good to see you. Say hi to Steve for us.
I will.
Okay, bye-bye.
Bye.